So one other thing I would like to mention here, y prime is the same thing with the notation f prime of x, and it's also the same thing with the notation the derivative of y, and y is also f, right? The derivative of y with respect to x, dy over dx, the derivative of y with respect to x. First of all, this notation tells me a lot. What does it say? It says that y is a function of x, and I need to differentiate y with respect to x. You can say, why do we need three notations? Well, let's discuss these two first. From the very beginning of your algebra experience, you always knew that f of x and y mean the same thing. This is convenient when I talk about a point, and this is convenient when I talk about a function, but they mean the same thing. It's easier to say find f of 3 than say find y when x is 3. So that's why we use two notations. They are the same, but they have different usage. Now, what's with all this? Well, we have to learn this notation is useful in other situations. And we are going to get to this, to the use of this, very soon in this chapter, in chapter 3. So I want you to understand that these are interchangeable. They all mean the same thing. Now, when you get to, for example, multivariate calculus, you will understand that this notation of normal D means that the function has only one variable. There are other notations, you don't have to write this down. So for example, this. Notice that this is not the same D. This means we are differentiating function the second derivative. We are finding the second derivative of the function with respect to x. But this function, because this is not this normal D, but a squiggly D, it means that this function has more than one variable. So forget about this now. This tells us, because in this class we are not going to deal with multivariable calculus. So this notation specifically says y is a function of x only. This notation says, yes, you have to differentiate with x, but there are other variables in f, one or more. So understand that these all mean the same thing, and this means y is a function of x only. Okay, so now, every time I'm asked to find a function, a derivative of a function, I have steps to go through, like when I'm asked to find the limit. There are very few exceptions in which I will not plug in to see what the case is, right? We have the absolute value, have the square root, and other functions. But in general, we have to plug it in. Why am I saying that? Because here, when I'm asked to differentiate, I will always take a moment and analyze the function. Can I simplify it? Can I simplify it so I make my life easier? I will always ask myself that question. No, for 3e to dx there is nothing I can do, but for this piece, yes. I don't want to differentiate something like this. When I can differentiate something like 4 multiplied by what? X to which power? Anyone?
Square root cube.
Careful. X to which power? 1 over the... Yes? Yes? Give it a shot.
Just cube.
Say it again.
Say cube, just cube.
So notice that the cube root of x is in the denominator. And I want to write 4 times x to which power? Okay, maybe that's not clear. Let me write it here. I want 1 over the cube root of x to be written as x to a power. Extremely important. If I can do this...
The 1/3 power?
Say it again.
The 1/3 power.
But can 1 over x be the same with x?
Yeah, isn't 1 over x equal to x to the 1/2 power?
But that will be the square root. If I have 1 over the square root, then it's x to which power? So what I'm asking is 1/2 the same thing with 2? We wish. So 1/2 cannot be written as 2, but 2 to which power? Anyone?
2 to the power of 0.
2 to the power of 0 is 1, as long as the base is not 0.
To the power of -1.
Thank you. So this must be -1/2, and this must be
-1/3.
that. Thank you very much. So it's 4 times x to -1/3. So whenever I'm asked to differentiate a function, first I will simplify it to make it easy for me to differentiate. So our new function is this: 3e to the x plus 4 times x to -1/3. And now I can differentiate. I can write y prime. I can write dy over dx. This is called Leibniz notation. Okay? It bears his name. Okay, so then I differentiate 3e to the x. What do I get? We differentiate 3e to the x. Anyone? Who would like to answer? If not, I'll go one by one. I need an answer, please. Please.
Is it not still 3e to the x?
That's all I want you to say. I have to write something. Awesome. Now we are differentiating this. Great job. Good. We're differentiating this. What do I have to write next?
I think I misunderstand. So when you say differentiate, can you explain what that means one more time?
We are using differentiation rules, not the definition, to find the derivative.
Okay. Thank you.
Thank you. So, how do I differentiate this? Anyone?
I think the 4 is a 4 because it's a constant multiple. And then we bring that down and subtract 1.
So you're saying 4 times -3 is -4/3, and you subtract 1 from, okay, good. So we copy, awesome. We copy x and subtract 1 from -1/3. When we subtract 1 from -1/3, what do we get?
-4/3.
That's it. So this is the derivative of the given function. Awesome. That's it. We don't need to do anything else.
I'm confused. How is the derivative of 3e to the x power still 3e to the x power?
Okay. Does that answer your question?
Yeah, that does that.
Awesome. If you don't ask questions, then I don't know whether we are following or you need help, or so please ask any question. Good. So again, now the floor is open to you. Whatever you would like to, we should look at a problem like this that has a ratio, or maybe this one. They're all the same. And as you see the notation now, dy over dx and dy over dt, which means y is a function of t, not of x. Dy over dx means y is a function of x only, not of t. So they're giving us a combination, and when they're asking us to find dy over dx, it means that t is a constant. If they're asking us to find dy over dt, it means that x is a constant. We can have, in this notation, we cannot have more than one variable. This is the notation for multiple variables, not this. So then the function has only one variable. Okay, do we choose? Do you want me to choose? If you want me to choose, I will choose 29. If you want to choose, you choose what you want. But we have to choose.
5,
Which one?
25.
25. Very good. Let's take a look at 25. Good pick. Same thing. G of r equals 3r to 3 halves plus r to 5 halves divided by r. Perfect. So, again, I know I sound like a broken record, but it's the only way. Trust me. Again, when I find a limit, I plug it in first. I have to, because I have no idea what I'm dealing with. Okay? When I am asked to find the derivative, I always try to simplify the function. I don't just jump in and say, hey, let's find the derivative. No, no. I look at the function and see, can I do something to help myself find the derivative of this? Yes, and I can. And here's what I can do. And again, this is a very important concept. So if I have a plus b, or minus, it doesn't matter, divided by c, this can be replaced by a over c plus b over c. Of course, if I have minus here, I have minus here, it doesn't matter. And this is again a dynamic situation. If I have this, I can come up with this. If I have this, I can come up with this. So this was the same type of property. That this is, it's very important. Every time I present this to my students, I show the equivalency from left to right and from right to left. You know this symbol now from the epsilon delta definition. This means this, this means this. So the same thing here. In this situation, this means this, this means this. Why? Why I can do this? Only because the denominator is one term. One. If I have this situation, a plus b over c plus d, I cannot do anything. Because the denominator has two terms or more. But as long as the denominator has one term, I can always, if it's convenient for me, I can always present it like this. If I have this, if it's convenient for me to differentiate better, I can write this, whichever I prefer. But if I have two or more terms, it's dead in the water. I can't do anything. With one term, I can. I can separate. If I have three numerators, then I will have 3 fractions. If I have 4 numerators, then I have 4 fractions. But here I have 2, that's why I presented it with 2. And yes, I will rewrite it as copy the base, and this over this will have r to 3 halves minus 1. Maybe I should write, let me write the intermediate step. I want to write the intermediate step before I do that. So I'll use a triangle this time. Follow the triangle. So 3r to 3 halves over r plus 5r to 5 halves over r. And we know one other property of the exponential rules. Copy the base and subtract from the power of the numerator, subtract the power of the denominator. So the first fraction becomes 3r to 3 halves minus 1, and the other one r to 5 halves minus 1. This is way more difficult than this to differentiate. Of course, it's not cleaned up yet, but it will be. But this will be much easier to differentiate. So how much is 3 halves minus 1, and how much is 5 halves minus 1? And then we can differentiate afterwards. So notice, all this was preparation. I did not find the derivative. I prepared the function the way I like it to be. So then I copy 3. Can anyone give us this? R to which power?
1/2.
Yes, 3 halves minus 1 is 1/2. And plus R, 5 halves minus 1 is
3/2.
awesome. So all this work was just prepping the function. So now I'm ready to differentiate. So can anyone differentiate the first part and differentiate the second part? So G prime of R.
The first part is 3/2 R to 1/2, negative 1/2 power.
Yes, because 1/2 minus 1 will be negative 1/2. Very good. Plus. Awesome. Brilliant. And the second one? Anyone? Anyone?
Yeah, 3/2 R to the 1/2 power.
Yes, because 3 halves minus 1 is 1/2. And this is it. In certain situations, we will want to further simplify this, and we will, because later on in chapter 4 you will see why, actually. So what I would like to do here, at this point it's okay to leave it alone, but I just want to emphasize, look at these two terms. What do they have in common? And this is something from pre-calculus that I hope you remember. If not, we'll review it right now. What is the common factor here that I can pull out immediately?
The coefficients of 3/2.
Excellent. And now let's take a look. Both terms have R in common. I have to choose the smallest power. I know it's a silly question. Which one is the smallest power from negative 1/2 and 1/2? That's not a calculus question. So what is it? What is the smallest power?
Negative 1/2.
Perfect. So I put it in. So let's see what we have in parentheses. Notice that we have two terms, and we have to have two terms in here. I have plus, I have to have plus. So 3/2 is out. R to negative 1/2 is out. What is left here? Please do not say 0, because this times 0 will not give us this. This times something will give us this term.
One.
Exactly. 3/2 is out. I have here R to 1/2. From power 1/2, I have to subtract the power that I took out. So R stays to what power?
One.
Exactly 1. See how useful this is? The answer is no. You cannot see it because we haven't gotten to that part in the course yet. So this can be rewritten as 3 R plus 1 divided by 2 the square root of R. This is useful for what we are going to look at in chapter 4. For now you can say this is okay, but later on it will not. And I don't want to come back and say, see, I told you, and you'll say, oh, but you never showed us, right? You told us to finish, to end here and stop here. Yes, for now. But this is not correct till we simplify it fully for what we are looking for in chapter 4. So please understand these steps. This is no calculus. This is just algebra here. And pre-calculus. Okay. I think we should move on, but if anything else catches your eye, we can look at it. I like to look at an equation of a line. So let's find an equation. We can go back to, you said 39? This one?
Yeah.
Okay, it's a very good one. Yes, let's do that. I agree. So let me